So the next couple examples we'll do in breakout rooms, the collection of sets are a collection of intervals of the real line. And so it's good for us to just remember how we use notation to describe intervals of the real line. And so there's these three different kinds of delimiters that get used in talking about sets, right? We have the curly braces, and we know what the curly braces mean by now. Curly braces mean literally, I'm just going to list all of the elements that belong to my set in between the curly braces. And that's what curly braces are going to mean. It's a roster. It's a list of all elements. You can't see me writing, but I'll show you in a moment. And so then the other two different pairs of delimiters that get used are the round parentheses and the square brackets. And those are both used to talk about intervals on the real line. And so they have a very specific meaning that's different from one another. So the round parentheses are for an interval of real numbers, first of all. And the same is true for the square brackets. So those are both, anytime you see square brackets or you see round parentheses, we're talking about a piece of the real number line. That's kind of another way to think about that. And the distinction between the two of them, as you were alluding to before, is that one of them is used when we want to include the numbers that are at the endpoints, and the other is used when we don't want to include the numbers that are at the endpoints. So it's the round parentheses that get used to exclude an endpoint, and square brackets when we include an endpoint. So just as a quick example, let's suppose that I'm looking at the real number line, and maybe I want to do something like, solve the inequality -6 is less than or equal to x minus 4 is less than 10 or something, right? So I have this compound inequality. I try to solve it. I add 4 to all three sides of this inequality, which preserves the sense of the inequality, so we don't have to reverse anything. Plus 4. And so I end up getting -2 is less than or equal to x minus 4. Sorry, no, is less than or equal to x is less than 14, right? And so what this is kind of telling me, right, is that the x's which solve this inequality are those x's which are greater than or equal to -2, and also which are less than but not equal to 14. So if I diagram this out on my real number line, typically what I do is I draw a diagram that looks something like this. I'll put like an open circle down here at -2. And then I've got -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 14 is up here. And when I get to 14, instead of using an open circle, typically what we do in a diagram is we'll just fill in that circle as a visual way to kind of cue ourselves to the fact that we want 14 to belong to my set, but we don't want -2 to belong to my set. And then I'll just sort of shade in the piece in between. And so here is kind of a visual of what this set looks like. And then when it comes to actually expressing it using this interval notation, in interval notation we'll write this as -2, 14. So that tells me what's the left-hand endpoint, what's the right-hand endpoint, comma in between. And then we'll use on the right-hand side, on the 14, because it's included, because, oops, wait, I did this backwards. Sorry, my apologies. Rewind the video and forget what I said. I meant to draw it like that. The 2 was not included. Sorry, the 2 was included, but the 14 was not. And looking back here, right, greater than and equal to -2 are included, but less than 14 but not equal to 14 is included. So on the 14, I'll use the round parentheses to indicate that we're excluding that number. And on the -2, we'll use a square bracket to indicate that we're including. So one other way to look at this is that parentheses and open circles and strict inequality signs, less than, greater than, those tend to go together with one another. And then the square brackets, the permissive square brackets and filled in circles, and the permissive inequality signs, greater than or equal to, less than or equal to, that those tend to go together when you see them as well. So that can help you to sort of build up a set of mental cues for that. So in question number 2, we're indexing a collection of sets using the natural numbers as the index set. And the sets that we're building are -n, n, an open interval, which is a subset of the real line. And I use the word open here because what I'm thinking of is I'm thinking of not including either of the endpoints. So -n and n are not included as endpoints in these intervals. So again, open circles, round parentheses, less than and greater than, strict inequality signs. Those all go together in my mind when we're doing this. So my diagram for what these ANs would look like might be something like this. So we're indexing them on the natural numbers, which actually means we have a least value for n, right? N is 1, is the smallest one that I can do. And then maybe let's also list a couple more, diagram them out. N equals 2, n equals 3. So here, a sub n is the open interval -n to n. And so n equals 1 would be talking about the set -1, 1. Right. And so that set is the interval of the real numbers that has as its endpoints -1 and 1, and whose endpoints are not included in that set. So I'll kind of sketch it out here looking like an open interval. So there's my a sub 1. It goes from -1 to +1, and it includes neither of those endpoints. Now let's climb the ladder a little bit. If I go up to n equals 2, a sub 2 is going to be -2, 2. So it's also an open interval, open on both ends. And this time it extends from -2 to 2, but it also does not include either one of those endpoints. Open circle here, open circle there. And I'll kind of write down here, -2, +2. Okay. So there's the second set in my collection. And so now you're probably getting a feel for what the general pattern looks like for the relationship of these sets to one another. The third set, a sub 3, is -3 to 3, not including either endpoint. -3 to +3. Right. And so on, and so on. And since this collection is indexed by the natural numbers, we're not going to have infinitely many more going the other direction. We don't have an a0 or an a-1 or so on and so forth, right? We just have these sort of going upward from here. And so any question that I ask about the infinite union or the infinite intersection, I can kind of imagine that I'm standing here on the real line and looking up, right? And asking, well, what elements are in the sets that I see when I look up? If I want to belong to the infinite union, I just need to see one set when I look up. If I want to belong to the infinite intersection, I need to be able to see every single set in the collection when I look up. So there's the setup for problem number 2. And 3 is not that different. In number 3, we have a set of intervals, except this set is a set of what's called half-open intervals. So these are the b sub n's. And this is written as 0, 1 over n, with a round parentheses around the 1 over n, and a square bracket on the 0. So again, let's sort of build a diagram of what this thing would look like for the first few of these b sub n's. So when n is equal to 1, we're talking about the set square bracket 0, 1 divided by 1, round parentheses. So 0, 1 with a square bracket on the 0 and a round parentheses on the 1. So I'll kind of draw that as a filled in circle here at 0 and an open circle at 1 and everything in between. The everything in between is what makes this an interval of the real line. So there's a picture of what the first set in my collection looks like. And then we'll just sort of climb the ladder again. When n equals 2, the left-hand endpoint is still 0. The right-hand endpoint is 1 over 2. So this is an interval that includes the left endpoint 0, and which has a right endpoint of 1/2, but which doesn't include 1/2. So there's my set B2. And if you do a couple more, you'll start to see the pattern. So B3 is going to have 0 as its left endpoint, once again included, but 1/3 is now going to be the new right-hand endpoint, not included. There's my B3. And so on and so on. So here's the picture for what these sets are going to look like. And so when it comes time to figure out the infinite union and the infinite intersection, again, imagine yourself standing somewhere on the real line and looking up and saying, do I see at least one set above me if I want to belong to the infinite union? Or do I see every single set above me when I look up? That's what I ask when I want to belong to the infinite intersection. So in problem number 3, you're analyzing this collection, infinite collection of what we call half-open intervals. Each one of them has a lower endpoint of 0, which is included in it, and it has an upper endpoint that follows the sequence 1 over n. So we start with upper endpoint being 1, and then 1/2, and then 1/3, and so on and so forth. And those endpoints are all not included in their individual sets. And so I just want to check in on what we got for the infinite union and for the infinite intersection. And looking on the Jamboard, the assertion here that's being made is that the infinite union over all n's in the natural numbers of b sub n is the half-open interval from 0 to 1, and that the infinite intersection, I'll just write this down on my board and then we'll go back to it, and the infinite intersection actually is what we call a singleton set. It's a set that includes only a single element, which is why you use curly brackets there, and that single element is 0. So there were the conclusions that you wished to make. So how did you come to those conclusions? How do we know, for example, that the infinite union consists of the half-open interval from 0 to 1? So one of the things that's nice about the sets in this collection, as well as in the other collection that we're looking at here, is that they have this nice monotone property. They're nested. Each of the sets in this collection is a subset of the one that came before it, right? B2 is a subset of B1. B3 is a subset of B2. And so as we progress up the natural numbers, we have this idea that you were talking about, that the sets are just kind of shrinking inside themselves the higher up that we go. And so the union of them all is just going to be the same thing as the largest one, in a sense, right? Because all of the smaller ones are just located within that largest one. And so this open interval from the half-open interval from 0 to 1 ends up being the infinite union, because at any place on the real number line from 0, inclusive of 0, up to 1, but not inclusive of 1, anywhere that I stand in that set, if I look up, I'm going to see at least one of the sets in this collection above me. Right? So the infinite union ends up being the largest of these sets, the interval from 0 to 1, including 0. And that same nestedness also helps us with the intersection question. But actually, I want to jump over to the other one of these examples to look at that intersection question first. So can somebody from group 2 tell me about the intersection, the infinite intersection that you got for this set, this collection of sets? The question of infinite intersection is a question of where do all of the sets in my collection agree with one another, right? What elements do all the sets in my collection have in common? And because we have this nice nesting property again, except that it's actually the opposite nesting property as we were looking at for the other one, here each set in my collection is a subset of the next one. So -1, 1 is a subset of -2, 2, which is a subset of -3, 3, and all the way up. And so I will find my intersection at exactly that place which is the smallest one of my sets in my collection, right? -1 to 1. Because if I'm standing at any real number between -1 and 1 on my real line, exclusive of the endpoints, and I look up, I'm going to see every single one of the sets in my collection over my head, right? So -1, 1 is a subset of the infinite intersection for that reason. And anything outside of -1, 1 will not be a part of this infinite collection, because in particular, it's not going to be a member of the first one of these sets, right? So the elements which belong to the infinite intersection consist of -1 to 1 and nothing else outside of -1 to 1. So there, the infinite intersection is the smallest one of these, for the same reason that the infinite union of this set of examples was the biggest one of these three, just because of that nice way in which these sets stack together like a Russian nesting doll, in a way, right? Okay, so then the slightly more interesting part of each of these problems was the other one. So let's start with the infinite union of this set of examples. So here, all of my sets were getting bigger the further that I went up, right? They were nesting inside one another that way. What did we decide was the infinite union of this collection?
Open brackets, I'm sorry, open parentheses, negative infinity to infinity.
Negative infinity to infinity. In other words, the entirety of the real line. So there's a bunch of different ways to write that. One is to write it using an open interval from -infinity to infinity. The other way is just to write it as the set of real numbers. So what you're saying is no matter where I stand on this real number line, if I look up, I'm going to see at least one set above my head. What would be an example of a set? If you choose any real number arbitrarily, then which one of these sets will I know that I can find x in? Just looking at how this collection of sets is defined. So every real number belongs to this infinite union, because all we have to do is just look up and we'll see at least one of the sets in my collection sitting above me. Just by rounding myself up to the next largest integer in absolute value, I'm going to belong to that set in the collection. So that's kind of an interesting behavior. The other interesting behavior is happening here with the infinite intersection of this nested collection of half-open intervals. So each of my sets in my collection was a half-open interval of the real numbers. But when we take the infinite intersection, we end up with something that actually doesn't look much like an interval at all. It's a set which has a single element in it. We show the whole roster here. So tell me about the reasoning. How do we know that this infinite intersection consists only of the real number 0? So there's sort of two questions. The first is, how do we know that 0 belongs in this intersection? And that's made explicit by how we've defined these sets, right? 0 is intentionally included in each one of the half-open intervals that make up my collection. So we know 0 is going to belong to the infinite intersection because we know it belongs to every single one of my sets because explicitly we've said each one of my sets includes 0 at its left endpoint. So then the interesting question is, why doesn't anything else belong to this set besides 0? Because there's sort of this idea that you expressed very well that the right-hand endpoints here are marching closer and closer down towards 0 arbitrarily far. They never actually arrive at 0 at any finite value of n, but we know that they're sort of getting closer. They're approaching 0. In calculus, we would say that the limit of that sequence of right-hand endpoints converges to 0, right? And so one idea that sometimes people will bring into this is, well, isn't there some number that's so close to 0 that it's not equal to 0, but it's somehow small enough that it gets to be a part of this infinite intersection? A number which is positive, and yet which is smaller than any other positive number. Well, the real number system, unfortunately, doesn't have such a thing by a property that we call the Archimedes axiom, or the Archimedean property. Basically, it goes like this. Let's suppose that I'm any small positive number. And for historical reasons, we like to call numbers like that epsilon, the Greek letter epsilon. Say I'm some really small number. Can I find some set which I don't belong to when I look up? Right. Well, it's the same kind of argument as we used in the other problem. We just need to be able to find one of my sets that's so small, right, that epsilon is not going to be included within it. So what I can do is I can find a 1 over capital N. I'm going to call this set up here B sub capital N, right? Its right-hand endpoint is 1 over capital N. I just need to find a 1 over capital N which is less than epsilon. If I can do that, then epsilon doesn't belong to my B sub capital N, and so therefore doesn't belong to the intersection. And so what if we were to write this as a proof, which we won't do today, but it would look something like this. For any positive number epsilon, we can find there exists a natural number n, capital N, such that 1 over n is less than epsilon. This thing that I just wrote down is called the Archimedes axiom, or the Archimedean principle. This is something that's true for the real numbers. It's probably the most important thing to know about the real numbers when you go to actually take an Introduction to Analysis course, where this is a really powerful fact to be able to use. But you can kind of imagine how we would do it. If I want to find this capital N such that 1 over n is less than epsilon, what I might do is just take the reciprocal on both sides of this inequality. I just need to find a natural number which is greater than 1 over epsilon. And so I would just do something like set n to be 1 over epsilon, but rounded up to the next largest natural number. Right? So if you give me a number like 0.01, right, then I know that that number is not going to belong to the set where if I take its reciprocal, I would get 100. Take the next largest integer than 100, that's 100. So 0.01 would not belong to B sub 100 in this collection, right? Because B sub 100 would be from 0 to 0.01, but not inclusive of 0.01. And so it would fail to belong to that set, so it fails to belong to the infinite intersection. So that's a very long-winded argument for how I'm agreeing with you that the infinite intersection of this consists only of the number 0.